So bulk synchronization delays will basically mean that you will be as slow as your slowest thread, and that thread can be because it's processing more data, or it can be just because, well, but tough luck, you just ended up in the wrong queue. And this will be also manifested if you have a producer-consumer model. So if suppose that you're, for example, feeding a buffer with some input, and some other threads are reading from that buffer the output to process the output, for example. Then in the producer-consumer model, if you have such if you have oblivious scheduling, then you might end up basically having delays in your producer-consumer model, because the whole scheduler is completely oblivious on what it should run before, which threads should run basically first, in terms of because you have these chained threads basically. It can be also that the critical path will be delayed, and the critical path is parts of the code on which everything else will depend. So if you have delays in your critical path, you will end up with significant delays everywhere in your system. And you might have preemption of lock holders also, because as the scheduler is completely oblivious on which threads belong to which applications, then a thread can acquire a lock on a much needed resource and basically get preempted, because, well, it's round robin in MFQ and in the same priority, and it will get evicted because of, well, other threads in need of or other threads time slice starting, and it just gets evicted while holding the lock, and the other threads cannot proceed because you have a lock being held by a process that is waiting, by a thread that is waiting in the waiting queue. So these are all manifestations of what could go wrong if you have oblivious scheduling. So the way that most people would actually handle, for example, threaded multi applications on most operating systems. Threaded multi-threaded applications on a multi-processor machine, on a multi-core machine, is that you will use what is called gang scheduling, and you will basically try to schedule the same task at the same time everywhere. And there might be some issues with gang scheduling, because if you have, for example, single-threaded processes, their performance might get hurt by basically having gang scheduling running on occupying all cores, while single-threaded processes do not really run. There is also the law of diminishing returns, basically. So if you have an application that has very limited parallelism, then adding more processors will not really improve your performance. And this is, if you look at the curves on the left hand side, then the lower curve basically tells you that no matter how many processors you will add, you will not get really an improve in response time. There are perfectly parallel processes, and these are very hard to write and almost non-existent in nature. Not in nature, but rather in most the programs that we write, basically. And in that case, you will basically gain linear gains by adding more processors to your system. But there is also some applications that might benefit from extra processors until some level, and this is the law of diminishing returns. And in that case, you would basically want to work or to parallelize, as long as parallelism gives you linear or almost linear performance increases. You'll get losses maybe in the order of 5 or 10%, but you can't tolerate that because you'll get a boost of 60%. But if you're adding an extra processor, so instead of running in just one core, you're running now on 2 cores, and speed up you're getting is 10%, then that's basically useless. Okay. When you are also, most processing, most operating systems, when it comes to thread preemption of lock holders, for example, they would also implement a mechanism such that the processor will actually a process that starts and finds that from, for example, higher from higher priority job that starts and finds out that well, I cannot proceed because a thread from a lower priority queue acquired the lock. I mean, then what would happen is that the operating system will basically delegate the priority by basically running the low priority thread that acquired the lock and slept or was preempted until it releases the lock, and then basically stop the lower priority thread and rerun the higher priority thread. And there's also scheduler activations that can basically provide the applications with upcalls to make the application aware that there is now a possibility for the application to improve its scheduling. Okay, last thing I'm going to talk about before talking about how or one of the last things that I'm going to talk about before we jump into how the Linux scheduler is actually built is energy aware scheduling. And basically I'm not going to go into the details of how energy aware scheduling is done, but I'm just going to put a few notes on how people consider these problems. And the problem is that basically on laptops, for example, or on mobile phones, your scheduling will affect how much energy you're basically using from the battery. And if so, and that's something that you can actually see in some between different mobile phones and between different, for example, if you upgrade between different operating system versions, so different Android versions or different iOS versions or different Windows versions on your mobile phone, this can actually affect your energy consumption if you have gone through that. And energy consumption, energy aware scheduling is basically now being handled by different means. The first one is basically in the processor design itself. So the processor provides the scheduler with capabilities to reduce the energy consumed in the system. One of these is the dynamic voltage and frequency scaling mechanism, DVFS. And dynamic voltage and frequency scaling basically reduces, I mean, if there is not too much load on your system, on your laptop or on your mobile phone, then it will clock down your processor. And if it clocks down the processor, so if the processor is supposed to run at 3 gigahertz, for example, it can clock it down to 1 gigahertz or lower, and then what you will get is basically a significant reduction in the amount of power or energy you're drawing from the battery. There is a more recent technique that is more fine grains, that is called RAPL, and RAPL is you can actually try it on almost all computers since 2000 and all processors since 2011 roughly, and it provides you with a mechanism, or provides the either you through an API, or it provides also the operating system with a mechanism to basically say that I want to run at 10 watts now, or something like that. And there are other trends, for example, like using ARM cores, or what is called Wimpy cores sometimes. So ARM cores are called Wimpy cores, and Wimpy cores typically use significantly less power compared to other processors like Intel processors. And this is why, for example, you have now the Intel Atom, and you have a few of these processors that are really simple and really weak, but really energy efficient. And this is why most mobiles run on ARM processors, because they are just very power efficient. Then, given the processor design, the scheduler can do some changes using the primitives that were provided by the processor, such as shutting down some parts of the computer, shutting down, for example, a memory bus, or shutting down, you can't even shut parts of your processor on some processor designs. Most new processors will allow you to do this. And when you think about, for example, that the new Intel Xeons, Broadwell, they are no longer just a processor, but they come with an FPGA, a field programmable gate array, so that you can program also the hardware. And you might want to look what an FPGA is if you do not know what an FPGA is. Then you might even shut the FPGA, you might shut a coprocessor, you might shut down the GPU, and so on. And you might also start shutting down other resources, like, for example, your Wi-Fi, or on your mobile, your cell phone network interface, which is actually quite typical that your mobile phone does. It actually, when there is good coverage in the area, then your mobile phone will sleep basically for a while. The cell phone network adapter interface will basically sleep for a while. Well, a few milliseconds is a while, or a few seconds. If it's a second even, you wouldn't notice. And every some predefined time, it will wake up, send a beacon signal, send a signal basically to the mobile tower, telling it, "Oh, I'm alive," and then the mobile tower will reply. So real-time scheduling, and we'll talk quite a bit more about real-time scheduling in the Linux kernel. And these are basically softwares that you would use for example, for controlling aeroplanes, right? You have an operating system on an aeroplane, on a Saab, for example. On the Saabs that are owned by BRA Aviation, we actually had once a lecture by some of the people who build these these airplanes, and it's just an operating system. They have an operating system running on their airplanes, and on both military and non-military planes, you will have these real-time schedulers basically to make sure that the plane flies. You also have some operating systems in your car. For example, recent BMW or recent Mercedes, recent Volvo will have hundreds of computers that will run a distributed operating system typically. So you would need, you wouldn't want your anti-lock braking system or your anti-skid system to basically be preempted because right now your radio is going to fire up or something while you're going to slide into the lake, right? Similarly, even your movie on the computer, if you're playing a movie on the computer, you want real time. If the video is rendered too slowly for you to see, then you would basically have a very bad quality of experience, which is you'll have jitter, and you'll start seeing breaks in your video. You might even start seeing the pixels in the video in a bad way. And similarly, if you're playing Half-Life and you shoot an enemy, then your fired shot, you do not want it to, like, the effect to appear 5 seconds later, because, well, that's just meaningless. So real-time scheduling, you will always have some real time, you'll have some deadline that you want your scheduler to meet, okay? And to meet that schedule, to meet that deadline, the scheduler typically does one of three things. The first one is to over provision, basically have a bit of extra resources almost always to be able to run at any time you ask for real-time task to be scheduled. The second one is basically to try to do scheduling based on earliest deadline first. So if you know that, well, the shot in Half-Life for a human player to be able to understand that, to feel the difference, we need, for example, the shot effect should take less than to 100 milliseconds. Then you basically know that this is the time span during which you can compute everything and run everything and show things on the screen to the human. Okay, and you can have something that's called priority donation to circumvent priority inversion. So if you have the multi-locking some application that holds a lock that you would need for your real-time schedule, you might do priority donation, basically give it higher priority to release the lock and then take it back to basically make sure that your deadline is met by making sure that nobody holds the locks that you need.